3. SQL's role. Used in both DDL and DML. Facilitates defining database structures, tables, views. Generates SQL statements for reports and controls resource access. 4. Procedural language extensions. Include languages like PL/SQL, C, Java, Visual Basic, and COBOL. Used to write data manipulation commands that are compiled for database access. 5. Data dictionary functions. Provides metadata on data items, their structure, and relationships. Automatically updates with database changes, removing the need for manual updates to application programs. 6. Data dictionary examples. DB_tables shows metadata about tables, e.g., number of columns, rows, primary keys. DB_tables_columns. Details about each column in the tables, e.g., column name, data type, length. 7. Data repository. Contains metadata about data models and interfaces. Used by case tools for schema development and is separate from the DBMS. These points outline the structure, functions, and components of a database system. 1. Components of a database system. Database. Stores data. DBMS. Database management system software that creates and manipulates the database. Data dictionary. Stores metadata. Hardware. Physical components needed to run the database system. 2. Database system purchase. Typically purchased from vendors like IBM, Microsoft, or Oracle rather than custom-built. 3. Ease of access. Database systems provide tools, query languages, report writers that enable end users to access and analyze data without needing to write complex programs. 4. Data integrity. Ensures data consistency, accuracy, and reliability by controlling redundancy. While redundancy is not eliminated, it is controlled through adherence to business rules and constraints. 5. Program data independence. Unlike file processing systems, database systems separate data from application programs. The DBMS manages data access using the data dictionary, which shields application programs from changes in data structure. 6. Data relatability. Database systems facilitate logical relationships between records from different files. Users can specify data to be combined, and the DBMS handles the integration, unlike file processing systems, which often require custom programming for such tasks. 1. Definition of models. Models are simplified representations of reality used to understand relationships. They can be physical, e.g., model aircraft, or mathematical, e.g., econometric, optimization, statistical models. Directed graphs, digraphs, are used in mathematical computing to model variable relationships. 2. Data models in database design. A data model represents real-world phenomena and is crucial in database design. Data models help describe both tangible, e.g., chairs, and intangible, e.g., departments, objects using descriptors. 3. Role of data models. Data models help in understanding data specifications, such as types, relationships, and constraints. They serve as blueprints for database design, ensuring that the database accurately reflects data requirements. 4. Database design process. Requirements specification identifies objectives, data, and process specifications through document reviews and user interviews. Data and process requirements. Data requirements are linked to process requirements, e.g., sales processes require data on customers' inventory. 5. Design phases and examples. Databases represent the universe of interest, varying in scope depending on the organization, e.g., different functions or product groups. The design process involves gathering and organizing user-specified restrictions, business rules, and defining how data will be used in various processes. 6. Separation of data and process requirements. Data requirements are derived separately from process requirements. Data requirements are illustrated through stories and examples in the book. These points outline the conceptual and practical importance of data models in the database design process. 1. Data modeling life cycle. Conceptual data modeling defines the data structure abstractly without considering physical storage or retrieval methods. Focuses on capturing business rules in detail. Logical data modeling builds on the conceptual model with technical details that are necessary for implementation. Physical data modeling finalizes how the data will be stored and accessed in the database. 2. Conceptual data modeling. Purpose: to describe the data structure and capture business rules without technology constraints. Outcome: produces a conceptual schema. Methods: includes entity relationship modeling, which is used in this book. 3. Modeling. Presentation layer model, used for communication with users, includes an diagram and semantic integrity constraints. Design-specific model contains technical details for database design and is used by database designers, not for user communication. 4. Validation. Ensures that the conceptual model accurately reflects all business rules and requirements. Involves checking that the model answers all questions posed in the requirements specification. 5. Example scenario. Entities, law firms, lawyers, clients, and lawsuits. Attributes: names, addresses, phone numbers, case numbers, etc. Business rules: some rules, e.g., gender can only be male or female, may not be captured directly in the diagram and need to be recorded in a semantic integrity constraints list. 6. Diagram. Components: includes entities, e.g., law_firm, lawyer, client, law_suit, and relationships, represented by diamonds. Purpose: to visually represent and communicate the business rules and data relationships. These points summarize the phases and processes involved in data modeling and database design, particularly focusing on conceptual data modeling with diagrams. 1. Purpose of logical data modeling. Converts a technology-independent conceptual schema into a technology-dependent schema. Aims to address incompatibilities and refine the design to reduce data redundancy. 2. Outcome. The result is the logical schema, which aligns with implementation technology like hierarchical, network, or relational models. The focus of this text is on the relational model. 3. Relational schema. Conversion. Each entity in the diagram is mapped to a relation schema in the relational model. Associations. Relationships are represented using relation schemas, with many-to-many, n. Relationships often expressed as separate relation schemas. Example: the vignettes model is mapped to a relational schema in Figure 1.8b. 4. Components of the relational schema are 1. Lawyer. Attributes: lyr_lf_name, lyr_name, lyr_emp#, etc. are 2. Law_suit. Attributes: ls_lf_name, ls_case_number, ls_case_type, etc. are 3. Involved_n. Attributes: l_cl_f_name, l_cl_l_name, l_ls_case_number, l_all. are 4. Client. Attributes: cl_name, cl_name, cl_gender, etc. are 5. Law_firm. Attributes: lf_name, lf_address. are 6. lf_location. Attributes: loc_lf_name, loc_location. 5. Normalization. Discussed in detail in subsequent chapters 6 through 9, which addresses the need to eliminate redundancy and improve the schema design. These points summarize the transition from conceptual to logical data modeling, focusing on creating a schema suitable for database implementation. Here are the key points for physical data modeling. 1. Objective. The main goal is to determine internal storage structures and access strategies for the database. 2. Storage technologies. RAID, redundant array of independent disks, uses multiple disk storage devices to act as a single high-performance logical disk through data striping, which distributes data across disks to improve performance. 3. Scope of the book. Focuses primarily on data modeling and database design, not physical design. Physical design details are covered in chapters 10 through 13. 4. Transformation to physical design. Involves converting the logical schema into a database language like SQL. SQL example, Figure 1.8c shows SQL statements using the data definition language, DDL, to create tables based on the relational schema. 5. Physical design steps. Creating database structure. Use DBMS tools to set up the database and design applications. Performance optimization. Ensure the database structure supports efficient performance based on the job mix, transactions, queries, etc. 6. 3 Schema architecture. The YNSI/Spark 3 schema architecture guides the data modeling process from conceptual through logical to physical design. This architecture underpins the progression through the book's chapters.